Linear equations. A very important concept in mathematics is that of linear equations. Already in high school, you learn about linear equations. And it is very likely that you have solved such an equation today.
Let's have a look at the theory.
Linear equations are extremely relevant, and we find situations where linear equations are applied virtually everywhere in our daily life. Think about predicting the weather, building bridges, buying and selling stocks, creating animations and games, or even searching on the internet. In all these cases, linear equations are being solved. In healthcare, linear equations are being used to predict how different medications may interact, or to prevent an overdose. The prediction of future weather is important information to you, but also crucial for agriculture and fields as defense, shipping, and aerospace. Weather forecasting is done by using satellites that provide images and data. This information is then used to solve linear equations that predict parameters like temperature, humidity, or rainfall. The reason why linear equations are so useful is because many complicated problems can be well approximated by systems of linear equations. Additionally, there exist also problems that are explicitly linear in nature. It is therefore hardly impossible to overstate the practical applications.
How can quantum solve this?
While linear equations form the most basic set of equations, they too can become hard to solve once a system has many parameters. A quantum computer that can efficiently solve linear equations would thus be extremely valuable. Quantum computers follows the rule of quantum mechanics, which is explicitly linear in nature. Hence, you could expect that a quantum computer might be able to solve linear systems very efficiently and much faster than we can do using classical computers. And indeed, this can be the case. For example, a quantum computer may make use of the HHL algorithm. This algorithm is named after its inventors, Harrow, Hasidim, and Lloyd. And this can solve linear systems exponentially faster than its classical counterpart. To illustrate how big a difference it is, let's take a system with 10,000 variables. The classical computer, in the best possible case, needs 10,000 steps to solve the linear system. However, the HHL algorithm only needs around 13 steps. This is a mind-boggling difference, and given the usefulness of linear systems, solving this algorithm on a quantum computer would bring about a revolution. Of course, there are a lot of challenges.
What are the caveats?
The HHL algorithm, in particular, has a lot of subtle caveats that makes applying it not straightforward. First, the algorithm does not actually yield the solution vector corresponding to the linear equation that we're after. Rather, it prepares a quantum state that is proportional to the solution, and finding the full solution would provide a large overhead. This means that we don't really have full knowledge of the solution, but rather have the ability to learn some aspects, or to ask a quantum mechanical question about the solution. A limitation is that we need that the entries of the matrix for the linear system are sparse. This means that we require that the matrix contains mostly zeros. Another limitation is that it must also satisfy robust invertibility. This is a strong technical condition and roughly means that the entries of the matrix must all be of approximately the same size. Perhaps the biggest challenge to solve is how to prepare the input vector. This will require either a quantum computer or quantum memory or QRAM. And preparing this is very complicated. To do so, we need to efficiently prepare and store the quantum state. This is a highly non-trivial task, and for general input data vectors, such a construction is not even possible. In conclusion, linear equations are used in many applications. And an exponential speedup in solving these systems using a quantum computer would thus be extremely relevant and could completely change our daily lives. However, the realization is highly non-trivial and most likely will apply to certain problems only. I guess one could say that this is a perfect example of high risk, high gain.